Just pointing out that we've got some variables here that are things that in general you're familiar with, but the specifics of them you're going to find are a little bit tricky. So for example, we've got an angle, but if you start messing around with this angle, which you can actually change just by like turning this, what you're going to see is things look a little funny. Like a 0-degree angle seems to be when the wheel is in this position, but if I move it even just 1 degree, look at how far my little critter goes. 1 degree is that much, and 2 degrees is that much, and 3 degrees is that much, and yeah, so one of the things, yeah.
The screen's frozen.
Oh. My goodness. Firing on all cylinders. Okay, let's go back. Okay, there's my 0. Here's 1. That looks a little weird, doesn't it? Here's 2. That looks a little weird. Here's 3. That looks really weird. And what's going on, of course, for those of you who have taken the geometry and trig and remember this, is we're using radians for our units of angles. And radians isn't exactly a unit, it's a ratio. It's a unitless ratio. Technically, 1 radian is a number with no unit associated with it at all. So we're going to be using radians when we think about angular motion. When we think about like a ramp that's tilted in 2-dimensional space, and we're thinking about an object's linear motion along that ramp, degrees are just as easy to use as radians, and you're more familiar with them. But with angular motion, it turns out the fact that radians are a ratio make it so that you can do some calculations a lot more easily and quickly. You're gonna ultimately save time. Where it becomes tricky is that in your brain, radians doesn't mean much. If I tell you something rotates, 1.8 radians, you're gonna be like, well, I don't know where that is. Or even if you're pretty good, some of you are still not to the point yet where I say, okay, 3 pi over 2 radians, and you're like, I know exactly where that is. So part of the fluency here is gonna be fluency with the unit of radians, recognizing that pi over 2 is a 90-degree angle. Pi, which is about 3, is a half a rotation. 3/2 pi is 270 degrees, and 2 pi, which is like 6 1/4, is 1 full rotation. So getting that in your brain so that you can like look at the displacements and angular velocities and have some idea of what they're telling you, that's going to be something that's worth your time to think about. The second thing is that when we start talking about things like linear velocity and angular velocity, which I hope you've had a chance to play around with at least a little bit, it's a little strange because if you look at, like if we start this thing rotating and we just let it move around, what you'll see is that actually it's not moving in a straight line. So if I want to think about this thing's angular velocity, I've got a number here. Doesn't mean much yet. Hopefully it will at some point. If I want to think about its linear velocity, how do we do that if it's not moving in a straight line? So one of the things that we do with these angular systems is we sort of shift back and forth between imagining that this circle was unwrapped and it was just moving like this and then starting back at the beginning and then moving like this and then starting back at the beginning. So it's like a piece of string that marks the path of this thing. We take the string and we straighten it out. When we think about linear velocity, we're thinking about distance along the curved string that might trail behind this creature as it moves. When we think about angular velocity, we're thinking about the rotations, something about the rotations that it's making or the angles that it's making. And that's a big shift. Thinking about motion in terms of angles is a big shift. if something moves 90 degrees, what does that look like and how far did it go? So let's think about that for a second. If something moves 90 degrees, what does that look like? Let's say that I have a object right here, and it moves 90 degrees. What does that look like? Where does it go? Any ideas? Yeah, Philip?
Well, wait, where does it start? Is it starting?
It starts here.
Does it have any velocity right now?
Oh, it doesn't matter. It's going to move 90
It
degrees.
just rotates then, like one, or maybe one rotation, like 90 degrees.
Oh yeah, that's interesting. Yeah, so if we wanted to think about this specific object and its rotation, we could rotate that object 90 degrees. And that's a great point. That's not the same as moving 90 degrees though. When something moves 90 degrees, it doesn't necessarily have to rotate at all. So what does it look like when something moves 90 degrees? We have to have a little bit more information to answer that question. If something is moving along a circular path, one thing that we have to know is how far away is it from the center of the circle. So if we have this object and we say, okay, the center of the circle is right here, then moving 90 degrees from here means it started here and it moves to here, such that this angle is 90 degrees. If it were located, if it were following a different circular path, like we could talk about this being the center of the circle, in which case this would be 90 degrees. This is 90 degrees in the opposite direction. But you can see that the location of this object, when drawn as an arc, is moving through an angle of 90 degrees as it goes from here to here. It's also moving through an angle of 90 degrees as it moves from here to here. But these distances aren't the same. Like if we make the circle smaller and smaller and smaller, this object will move a smaller and smaller linear distance. If we make the circle bigger and bigger, this object will move a different linear distance. And that's one of the big things that we have to account for in angular motion, rotational motion. So if I look at one of our setups that we were using yesterday, if you think about a point or an object located on the edge of this tube, if we rotate that, it's moving really far. If we were to imagine a string trailing from it, that string would be pretty long if the string starts at the edge of this tube. But if we had an object right here, like if there were a little spider right here, and it trailed a piece of web behind it as it spun around, that web wouldn't be very long. So when you have that angular motion, things don't move the same distance, even if they move through the same angle. And a lot of times, the way that we visualize this motion is just how it looks on the simulation that you're using. We visualize the motion as if we're looking down onto a circle. And then we can imagine things in different spots. I can imagine a thing right here. I can imagine a thing right here. And this thing, as it moves in a circle, is gonna move around like this. This thing, as it moves in a circle, is gonna move around like this. And you can see the blue dot is gonna move farther than the red dot if the circle makes one full rotation. And with the app itself, we have two things that we can use. Hang on, I have to make an adjustment here. The app itself has two things that we can use. It has a ladybug and it has a beetle. So we can move this back and we can put the beetle in a slightly different spot from our bug, and then we can give it a little bit of velocity, and you can see that they're both moving the exact same angular distance. And I didn't reset this, so there's some slight differences to begin with, but overall they're moving the same angular distance. But if you look at and think about the linear velocity, you can imagine that the beetle has to be moving faster. And in fact, you can see that here. If you look at this green arrow, it's showing you the instantaneous linear velocity. And the beetle is moving faster. As we speed up the angular velocity, both of those creatures will be moving at a faster linear velocity, but the beetle always is moving at a faster linear speed than the ladybug. And if we move the beetle to a different spot, then its linear velocity will change, but its angular velocity stays the same. So that's a really weird thing to think about. We now have two ways to describe the speed of objects that are spinning, rotating, moving along a circular path. One way is to think about how far they move in terms of meters and inches and centimeters. The other way is to think about how much of an angle they're moving through. If we think about how far they're moving in linear terms, we have a pretty good idea of what it would feel like. We know how fast 60 miles an hour is versus 20 miles an hour versus 5 miles an hour. If we think about it in terms of angles, we've got to know, if we really want to get a picture, we've got to know how far away something is from the center of the circle. If I say that something is moving at, 30 degrees per second, it's moving a lot faster if it's farther away from the center of the circle than it is if it's close. Things that are real close to the center of the circle can spin around quickly without moving very far. So part of what we're gonna be trying to do is tie all these things together. So keep working your way through the simulation. If you hadn't gotten to this point yet, you're now at this point where you're making observations about the critters. You're looking at how the location of the critters affects their linear velocity and what happens to the linear velocity as you change the angular velocity. And you can see that visually here. You can also see it graphically here. So let's see. Oh yeah, there we go. The dotted line is my, hang on. I need to, I need to reset this, sorry. I want to show you what this looks like if you start from the beginning. So I'm going to go back to my graphs, and then I'm going to put the beetle on there, and then I'm going to give it an angular velocity between 1 and 2, and now you can see that my beetle velocity is 5.2 meters per second. You might not be able to read that, but that's what it says. And my ladybug is about 3 meters per second. And you are just now starting to see the two lines. So there's my beetle, the dashed line. There's my ladybug, the solid line. If I increase the angular velocity, I'm going to increase both of those. If I decrease my angular velocity, I'm going to decrease both of those. But the beetle is always moving faster. If I move the beetle to the inside of the ladybug, Now they reverse. Now the beetle has a smaller linear velocity, but the angular velocity of both these creatures is the same. So we've got angular velocity here, linear velocity here. Okay, keep going. Let's see what you can do to continue to power through this simulation.